Hello everyone. Also, we'll continue the same topic, backstepping control. Here we're gonna have example and also MATLAB simulation. So let's first define the examples we are going to solve, and also we'll have the MATLAB simulation for the same example. Let us consider the following nonlinear system. Defined by x1 dot equal to ax1 plus x2 and x2 dot equal to u. So you can assume this is f of f1 x1 and this is u. There is no f2 terms, nonlinear functions, as you have done in the previous example. So here, let us define this, the equation number 1. And the question is design control u to stabilize x1 and x2. Okay. So here, there is no desired state to be tracked. Simply we'll design the control to stabilize x2, and x2 is going to control x1. So we'll start the problem. To solve the problem. So here, as you know, in the backstepping control, the second state is assumed to be virtual control, as you have done in the last lecture. So the second state is assumed to be virtual control, and which is going to control the x1 dynamics. So let's assume x2 equal to alpha 1. So alpha 1 with the virtual control. In this lecture, we'll go a little differently to solve this problem. How we can come up the error dynamics, and how can we use the error dynamics to improve the stability of the overall system. And considering this virtual control concept, the first subsystem can be written as the first hubs yields to be x1 dot equal to ax1 plus alpha 1. Now this is our step 1. Step 2, let us design virtual control to stabilize the x1 dynamics. Virtual control design. So here, let us design alpha 1 in such a way that x1 is stabilized. So let's choose alpha 1 equal to minus ax1 k1 x1. So if you substitute this dynamic, this equation, in this equation, so x1 dynamics will be stabilized. So let us define this, the two, equation number 2 and 3. Okay, or we can write here minus a plus k1 x1. So instead of this, let us define this 3, question number 3. Now step 3. Let us define the Lyapunov function as v1 equal to half x1 square, and v1 dot we can write x1 dot. In place of x1 we can write a x1 plus alpha 1, and in place of alpha 1 we can write a x1 minus a x1 minus k1 x1, and here we can write minus k1 x1 square. And if you notice this v dot is negative definite, we can say this is the stability can be checked for this particular expression. And for this we can write, if you now substitute this alpha 1 in this expression x1 dynamics, so now the closed loop system will be x1 dot equal to minus k1 x1, and this is, we can say here k1 is greater than 0, so the system is globally asymptotically stable. So now proceed for the second subsystem. As you have done in the last lecture, the state x2 must be equal to the virtual control alpha 1. But since they are starting from the defined initial condition, so we have to design a control force for x2 to track the virtual control alpha 1t. So here, step 4, design control to force x2t to track the virtual control alpha 1t, right? So for that, let us define the error. Define the error between actual state x2 and virtual control alpha 1 as e equal to x2 minus alpha 1. And let us define this equation number 4. Okay. And our aim is e tends to 0 as t tends to infinity. So if you can do this, we can say this x2 equal to alpha 1 over time. And also from equation 4, we can write x2 equal to e plus alpha 1. And here, what we'll do is we'll place. So in this example, we are going a little differently, as you have done in the previous example. The conceptually both are same thing. I think this approach is easier than the previous. Maybe you can find it. So here we can write, in place of alpha 1, we can substitute this expression here. So we can write e equal to minus a plus k1 x1. And let us define this equation number 3. Now, what you're going to do is this x2, okay, substituting equation 3, it should be equation 5 in equation 2, here in this expression, So in alpha 1, we'll put x2 dynamics. So we can write x1 dot equal to ax1 plus e minus a plus k1 x1. And from this we can write minus k1 x1 plus e. And this is defined by equation 4. So now if in this equation you can write the expression is written in the for x1 dynamics and the error. So this will be useful for deriving the stability part. This is equation 6. Now taking time derivative, equation 4, taking time derivative of equation 4, we can write e dot equal to x2 dot minus alpha 1 dot, and x2 dot in place of alpha 1 dot we can substitute alpha 1 dot, we can substitute this expression minus a plus k1 x1 dot we can write. So in this we can write plus a plus k1 x1 dot, and already we have the x1 dot dynamics, so we can write, so x1 dot dynamics is here, so we can write x2 dot plus a plus k1 minus kx1 plus e. And from this expression, we can write a plus k1 e minus, okay, also we can write, in x2 dot, we can write u plus a plus k1 minus k1 x1 plus e. And from this we can write a plus k1 e minus k1 a plus k1 x1 plus u. Now this e dot and this x1 dot, this expression and this expression will be using to derive the Lyapunov function. Okay, 7. Now step 5. Let us choose a Lyapunov function as v2 equal to v2 x1 and e equal to half x1 square plus half e square. So if you notice carefully, these two, equation number 6 and 7, the variable in the final expression are x1 and e only, no x2 term. And of course the control function. So now we'll take the time derivative of this. v2 dot equal to, we can write x1 dot plus e dot. So in place of x1, we already have the expression. We'll substitute this expression, right? So we can write x1 into minus k1 x1 plus e into e. In e dot, we can substitute this expression, right? So we can write a plus k1 e minus k1 into a plus k1 x1 and plus u. And from this we can write minus k1 x1 square plus e into x1 plus a plus k1 e minus k1 a plus k1 x1 plus u. So now in this expression, if you notice carefully, this is stabilizing function, negative definite, right? So now we have to choose in this expression u in such a way that all the terms are neglected, cancelled, and here we'll have something minus k2 e square. So we have to choose u such that this whole terms become negative definite. So let's write choose u in such a way that v2 dot less than equal to 0. So here we are choosing u as minus x1. So minus x1 it will cancel, right? And minus a plus k1 e plus k1 a plus k1 x1 and we can write another term minus k2e. Now, if you this is the term we have added here, and which will make this whole term minus k2 e square. Now, if you substitute this u here in this expression, so v dot we can write v2 dot. Let us define. This is equation number 8, and this is 9. Substituting equation 9 in equation 8, we can write v2 dot equal to, we can write minus k1 x1 square plus e into x1 plus a plus k1 e minus k1 a plus k1 x1 minus x1 minus a plus k1 e and minus k2e and minus k1 a plus k1 x1. Now from this we can write, so here this will cancel and this will cancel, this will, okay, it will be plus, and this is big plus actually, this is big plus, and this one will cancel. So here we can write the overall terms will to be k1 x1 square minus k2 e square. So this is, we can write, this is negative definite, and hence we can write, and here also k1 and k2 are greater than 0. So here we can write x1 of t, e of t goes to 0 as t tends to infinity for all initial values of x naught and e naught. Okay. Now, what about the x2? Here, actually, if you notice, you're proving x1 and xe, right? What about the x2 function? How it is going to 0? So if x1 is and e is going to 0, in that case, we can write we can say that we can say this whole term going to 0, right? This term going to 0, alpha 1 going to 0. Is alpha 1 going to 0, x2 is going to 0. So this is how we can say all the state are going to 0. So now we can write, okay, so this is the overall control in this particular example, this this is our overall control. Now we'll have the MATLAB code for this example, and we'll see how the state is going to 0. So this is the MATLAB code. So here we are simulating this. These are the initial values of x1, x2, and you are simulating the program for 5 seconds. This is OD45 to solve the differential equation. And this is the function backstepping we have used. And here we have chosen a equal to 3, k1 equal to 2, k2 equal to 2. So how these values are chosen, you can refer to the previous lecture. We came up some conditions. And this is how we are defining the variables. And here we are alpha 1, instead of alpha 1, we are writing lambda. And this lambda is nothing but alpha 1. And this is the overall control what you have obtained through for the stability analysis. This is the x dot dynamics. This is x1 dynamics, first equation. Second is an x2 dot dynamics. And this is the variables going to the function. And this is the figure to, these are labels to come up the figure for this particular example. And you can see that over time, the states are going to 0. And yeah, the system is stable for the particular control algorithm what you obtained in equation 9. This is basically stabilizing control, which make the system stable. So this is how we can write the MATLAB code for this particular example. So if you have any other dynamical system, you can easily come up the MATLAB code. So let's stop it here. We'll continue from the next lecture with different examples. Thank you.